22 disasters accounting for losses in excess of $1 billion each. That's a new record.
Hurricanes, storms, and wildfires are forcing Americans to abandon their homes.
Europe's weather has gone crazy this summer.
Hi, and welcome back to the second episode of this virtual field lab series, where we're investigating climate feedback loops and changes in the Earth's energy balance. I'm Mikhail Thompson, an architecture student at Washington University in St. Louis, and your climate host for this series. The rapid warming we are seeing on our planet is a result of an increasing amount of energy being absorbed by the Earth and trapped in the atmosphere. The increasing amount of energy being absorbed by the planet is impacting the frequency and intensity of wildfires, floods, hail, and other extreme weather events. As an architect, these factors play a huge role in how we think about designing homes and cities for a future with a warmer and more extreme climate. In the first episode, we investigated how the decreasing amount of sea ice around the North Pole is drastically increasing the amount of solar energy being absorbed by the oceans. We also looked at how carbon dioxide added to the atmosphere by burning fossil fuels is driving a feedback loop of warmer temperatures, less ice, and even more energy absorption. On the positive side, we also identified ways that we can break this feedback loop by rapidly moving from the expensive, antiquated energy system that relies on fossil fuels to a new energy system powered by cheap, clean energy alternatives like wind and solar. For the first time in history, the technology is available and the choice is actually ours to make. If our society chooses to move to a clean energy system, it will then be up to architects, engineers, and city planners like me to begin to design and build for what will be needed for a sustainable future. In the first episode, we investigated how the balance of energy was changing on the entire northern part of the planet. In this episode, we're going to travel to Greenland to see how smaller changes in the melting surface of this ice-covered island may also be impacting the balance of energy on the Earth. With that, let me pass you on to Dr. Alden Adolph, a climate scientist from Michigan Technological University. She is an expert in analyzing how the physics of snow and ice impact the energy balance of our changing planet.
Hi, I'm Alden Adolph, a climate scientist specializing in analyzing how much energy from the sun gets reflected off the snow and ice on our planet. In this episode, we're going to investigate how the balance of energy is changing on Greenland. Greenland is definitely a smaller scale than the entire area around the North Pole, but it's still large enough to have a global impact. We should probably start this episode with a quick review of my specialty, albedo. Albedo measures how much energy is reflected off of a surface. Something that is pure white would reflect back 100% of the energy that hits it, and is assigned an albedo number of 1 on the albedo scale. Something that's pure black would absorb all of the energy that strikes it. Since it reflects 0% of the incoming energy, it is assigned 0 on the albedo scale. In this episode, we are going to investigate how the energy balance of the Greenland ice sheet is changing. In the summer, melt ponds or lakes form in some locations on the ice sheet. You can see by this picture that melt ponds are much darker than the unmelted ice sheet. You can probably guess that the two surfaces have very different albedos, just like the polar ice and open oceans in episode 1. On average, the unmelted ice sheet on Greenland reflects about 60% of incoming solar radiation. This means on the albedo scale, it would be assigned a number of 0.6. The melt ponds, on the other hand, are much darker. They absorb 90% of the incoming sunlight and only reflect about 10%. This means they would be assigned an albedo of 0.1 on the albedo scale. We have used satellites since 1985 to monitor how many lakes form each summer on the surface of the ice sheet. Let's start this episode by writing down this question in your notebooks. How is the changing number of lakes on the surface of Greenland's ice sheet impacting the Earth's energy balance? Let me turn things over to Amy, and she will take you through our first investigation.
Thanks, Alden. I'm Amy, a senior at Grant High School in Sacramento, California. Alden asked if I could help investigate how changes in Arctic ice are affecting the energy balance of the planet. No problem. Let's start by getting familiar with the data we'll use for this investigation. Here's a map of the superglacial lakes, or melt ponds, that formed in 1985 on one area of the Greenland ice sheet. The lakes are shown on a topographic map. The numbers at the top of the map show the elevation of the ice sheet in meters above sea level. You can see that as the elevation increases, there are fewer and fewer melt ponds. This is expected since the temperature drops about 3.5 degrees Fahrenheit every time you go up about 200 meters higher on the ice sheet. This means that in general, we would expect it to be about 25 degrees Fahrenheit cooler at higher elevations of the ice sheet. The blue dots on the map show the maximum extent of summer melt ponds that form on the surface of the ice sheet. For this investigation, we'll count the number of lakes forming above the 1,200 meter elevation contour. Our data will start in 1985 and end in 2015. Let's make a data table in your notebooks to record the year as well as the number of lakes above 1,200 meters. When I count the lakes on the 1985 map, I would count 1 lake at the top, 2 in these middle areas, and 2 at the bottom. That would be a total of 7 melt ponds, or lakes, forming above 1,200 meters in 1985. Let's add this to our data table. Let's do one more together. In 1990, I see 1 lake at the top, 7 lakes in this cluster, 2 lakes in this lower area, and 7 more at the very bottom. This would be a total of 17 melt ponds, forming above the 1,200 meters in 1990. Next, I'll bring up maps for the other years of the study. I'll leave each map on the screen for about 10 seconds so you can count the melt ponds above 1,200 meters. If you need more time, pause the video. When you're finished making all of your measurements, I'll meet you back here to compare counts and build a graph of the data. Welcome back. Let's compare data. It was a little hard to count in 2014 and 2015, but here you can see my best estimates. Hopefully our data are similar. I think data tell a story best when they're displayed on a graph. In your notebook, let's build a graph with years on the x-axis and the number of lakes on the y-axis. Pause the video to build your own graph. When you're finished, hit play again, and we'll meet back here with Alden to see what she thinks of our data.
Thanks, Amy. When I plotted Amy's data on a graph, it looked something like this. When I look at the data, it definitely seems like the number of melt ponds is increasing over the 20 years of the study. In addition, 2 other things really caught my attention. First, it seems that the melt ponds are forming at progressively higher elevations. When the study started in 1985, there were no melt ponds above 1,400 meters. Just 30 years later, in 2015, there were even melt ponds above 1,600 meters. To me, this suggests that at the beginning of the study, the higher elevations were cold enough to stay frozen all summer. That definitely no longer seems to be true by 2015. The second thing I noticed was that in 2015, the number of melt ponds seemed to decrease. But if we look carefully at the maps of 2014 and 2015, it looks to my eye that even though there are fewer melt ponds in 2015, the ones that are there seem to be bigger. This makes me think that maybe we need to modify the question we're investigating. We asked how the changing number of lakes on Greenland's surface is impacting the Earth's energy balance. Based on the growing size of the melt ponds, a better question would probably be, how is the changing area of lakes on the surface of Greenland's ice sheet impacting the Earth's energy balance? Let's write this new question in your notebooks, and then I'll turn it back over to Amy to generate the data we need to answer this new modified question.
Thanks, Alden. To answer this new question, we'll need to calculate both the area of unmelted reflective ice as well as the area of less reflective, more energy-absorbing melt ponds. I scanned the melt pond maps into an AI tool. I asked the AI to calculate the area of the blue melt ponds in square kilometers for each year of the study. Here are the melt areas the AI tool calculated for each year of the study. Let's add these data to our table. Notice that these data suggest our hunch was correct. Even though there were fewer melt ponds in 2015, the total area of ice covered by melt ponds was greater than the melt area in 2014. Next, we should calculate the area of the highly reflective, high albedo, unmelted ice that remains each year. The entire study area is 6,200 square kilometers. The first two calculations will be exactly the same since the melt area didn't change. Pause the video and calculate the area of unmelted ice for the other years of the study. When you're done, hit play again and we will compare data. Welcome back. Here are my calculations for the area of unmelted ice for each year of the investigation. Now we should have what we need to build a graph that will tell us how Earth's energy balance is being affected by the melt lakes forming on the surface of Greenland's ice sheet. Let's make a graph with the area of reflective ice remaining on the y-axis and the year on the x-axis. Pause the video while you build your graph. Make sure to include a trend line that you think shows the story of the data. When you're done building your graph, hit play again and we can compare graphs. Welcome back. Here's what my graph and trend line looked like. I think it would be good to add one more set of data to our graph. Remember in episode 1, we found that the amount of energy being absorbed is increasing around the North Pole as more summer ice melts. At the same time this is happening, we have also been increasing the amount of heat trapping carbon dioxide in the atmosphere. Most people know that carbon dioxide is a big driver of our warming climate. Approximately 2/3 of the warming we are experiencing now is due to increasing amounts of carbon dioxide in the atmosphere. But there are also other greenhouse gases that can impact the amount of energy trapped by our atmosphere. Methane is a greenhouse gas that traps 28 times more energy per molecule compared to carbon dioxide. Methane is responsible for about 1/3 of the warming that has taken place in the last 100 years. Here's a graph showing how methane concentrations have changed in the atmosphere for the past 40 years. Let's use this graph to estimate the amount of planet-warming methane in the atmosphere for each year of the Greenland study. At the beginning of the study in 1985, I would estimate that the level of methane in the atmosphere was approximately 1,640 parts per billion. Next, pause the video and estimate the amount of methane in the atmosphere for the other years of the study. When you're finished, plot the data on your graph using the other y-axis to show the energy-trapping methane concentrations. You can also add the most recent 2022 methane data to your graph to help draw a more accurate trend line. Then respond to our investigation question by writing 2 things that you notice and 1 thing that you wonder. When you're finished, hit play again and you can meet Alden back here to compare data and graphs.
Humans have changed the energy balance and temperature of the planet by increasing the amount of greenhouse gases in the atmosphere. Current data indicate that the increased greenhouse gases in the atmosphere now trap almost 50% more energy than they did in 1990. In episode 1, we saw how the amount of carbon dioxide was increasing in the atmosphere. In this episode, we analyzed how methane levels in the atmosphere are changing. Here are my estimates and graph showing how the amount of methane in the atmosphere has changed during our period of study. One thing that I noticed from our graph is that just like in episode 1, we are increasing heat-trapping greenhouse gases, while at the same time, the areas of the planet that can reflect energy back into space are decreasing. This is another example of a feedback loop. Greenhouse gases trap heat and our planet warms. The higher temperatures cause the surface of the ice sheet on Greenland to melt, exposing more energy-absorbing melt ponds. The darker melt ponds absorb more energy, which means even more ice melts and even more energy is absorbed. As you can see in the diagram below, the cycle repeats, which is why we call this a feedback loop. These feedback loops have the ability to intensify the warming of the planet. While it can be a bit overwhelming to think about these spirals, there's reason to hope that we can break the cycle. These energy feedback cycles all start by adding greenhouse gases like carbon dioxide and methane to the atmosphere. We now have the ability to choose a cleaner future. In episode 1, we saw how scientists and engineers have developed alternatives to our old fossil fuel-based energy systems. Using wind and solar to generate electricity is now cheaper than burning coal and natural gas. Electric cars are also cheaper to own and operate than gasoline-powered cars, especially if you charge them using cheap, renewable energy sources. In this episode, we saw that the amount of methane, a super potent greenhouse gas, is rapidly increasing in the atmosphere. In 2022, methane accounted for 12% of all US greenhouse gas emissions from human activities. But, just like carbon dioxide, scientists and engineers have developed solutions that provide hope for the future if we choose to pursue them. Much of the 28% of the methane from natural gas and petroleum systems are simply leaks in pipelines. We now have satellite systems that can pinpoint those leaks. Take a look at these new images from the MethaneSat satellite. This new satellite can show how much methane is actively leaking from oil wells. The new data coming from MethaneSat suggests that the amount of methane leaking from fossil fuel production
could be 4 times what was estimated by the EPA.
If we choose to, we can hold petroleum companies accountable to stop leaks when producing and transporting methane. Even better, we can substitute green energy alternatives like wind and solar for methane. 25% of US methane emissions come from burping cows and decomposing manure. Here again, scientists and engineers have developed exciting alternatives. The methane from manure can be trapped and used to generate electricity instead of simply being allowed to escape into the atmosphere. We can also trap methane being released from landfills and use that methane to produce electricity. New research has also shown that we can decrease the amount of methane being released from burping cows. Some studies have shown that the methane from burping cows can be decreased by almost 82% by simply adding seaweed to their diets. This is another example of climate solutions that are there for us to implement if we simply make it a priority. This is where I find hope for the future. For the first time in human history, we can cut down carbon dioxide emissions by replacing fossil fuels with clean energy solutions, and we can save money while making that change. We can also cut methane emissions using new satellite technology to pinpoint leaks and use bioresearch on cows and manure to decrease methane production from agriculture. Cutting our greenhouse gas emissions using these money-saving and environmentally beneficial alternatives is a major way for us to break the feedback cycle and help get the energy balance of our planet back on track. Thanks for joining us on this second exploration of how feedback loops are impacting the Earth's energy balance. Come back for episode 3, where we will take a look at how microscopic changes on our ice sheets may be changing the planet's energy balance. We'll also look for more solutions that can provide hope for restoring the balance of energy on our planet.